Because the typical kinetic energy is much less than the energy of the Coulomb barrier, fusion must depend then on the probability of tunneling through the barrier. The particles coming here on the left on the region 1 meets the barrier, tunnels through the barrier, so you have the region 2 here where the amplitude of probability is being damped, and then finally transmits then for region 3 with a lower amplitude. We have that the wave to the left of the barrier can be expressed by a forward wave plus a wave that is being reflected. Let's call the amplitude of the incident wave to the left of the barrier A and the amplitude of the reflected wave B. And the transmitted region F, there is only a wave propagating to the right. Let's call this amplitude here F. So that the transmission is the amplitude of the transmitted wave over the amplitude of the incident wave. To find these amplitudes, we need to solve the Schrödinger equation. So let's isolate the Laplacian, divide both sides by psi, and the energy minus the potential is the kinetic energy. So this becomes simply p squared over h bar squared. Now, if the energy is less than the potential, which is what happens in the region 2, then the momentum is imaginary. We can use an ansatz for the wave function. Let's give it an amplitude and an exponential to the power of c over h bar. So if that is the wave function, then the derivative of the wave function is the wave function times c bar over c prime over h bar by the chain rule. And then the second derivative of the wave function is the derivative of the first derivative. It's going to give you psi over c prime squared over h bar squared plus the second derivative of c over h bar. Now, because h bar is a small number, the first term in the expansion is of leading order, right? H bar is a small number, so this number is much, much bigger than this number. That means that we can ignore the term of the second derivative of c. So if you substitute the second derivative of the wave function, the second derivative of the wave function, which is a Laplacian, over psi is equal to c prime squared over h bar squared. Substitute that in the Schrödinger equation, and that is simply c prime squared over h bar squared is equal to minus p squared over h bar squared. How nice is that? The h bar simply cancel out. So c prime squared is equal to minus p squared. That means that c is equal to minus the integral of the modulus of the momentum in radius. So substituting the c back in the ansatz, you have the psi is equal to the amplitude times the exponential minus the minus 1 over h bar times the integral of the modulus of the momentum in the r. The non-classical region goes from 0 to L, where there is an exponential decay in the amplitude. So the ratio of the amplitudes is going to be given by the exponential minus 1 over h bar and the integral from 0 to L of the momentum p in this region, which is going to give you the decay in the kinetic energy, therefore the decay in the amplitude. Now, because the transmission is f over a, then the probability, which is proportional to the transmission, is then proportional to the exponential minus twice h bar because of the squared, and the integral from 0 to L of the momentum, which we are going to write as q minus the energy. Since this is the module, the potential is bigger than the energy in the forbidden region. So this quantity is positive definite. Now, this is a definite integral, right? It goes from 0 to L. So it's going to give you a number. Turns out that this integral is equal to pi over 4. So the result is minus pi times L over h bar 2me. So you can write this L here in terms of the energy. Remember, L is the length of the forbidden region. Remember that V max, the maximum of the potential barrier, is E squared over R naught. And the beginning of the barrier is the first point where the energy is equal to the kinetic energy. So it's when V is equal to E, and that's equal to E squared over L plus R naught. We can approximate L to be much, much bigger than R naught, since the energy is so small that you are still very far away from the barrier. Once your kinetic energy becomes smaller than the potential energy of the barrier, so that you can write that the energy is equal to E squared over L. Actually, here let's reinstitute the fact that these don't need to be two protons. They can be any nucleus. They can be a nucleus of charge Ze times the charge of the electron, and an approaching charge of charge Z2 times the charge of the electron. So, in fact, this is the energy would not be E squared, it would be Z1, Z2, E squared over L. So you can write the L in terms of the energy is Z1, Z2, E squared over E. If you substitute this L into the probability, then you find the final form of the probability of quantum tunneling. Probability is proportional to the exponential of minus P Z1, Z2, E squared over H bar times the square root of 2m over E. You can notice that most quantities in this expression are constants. Then you can write the probability then is proportional to the exponential of minus b over the square root of e, where b is equal to square root of 2m pi over Planck constant bar times z1, z2, e squared. So this gives you the final form of the probability. This is the probability of quantum tunneling. The important part is that it scales with the exponential 1 minus the square root of the energy. So if you recall the cross-section that we were wanting to calculate, it was proportional to 1 over the energy times the probability. So we can now write that this cross-section is proportional to 1 over e times the exponential minus 1 over the square root of the energy.